Today we discuss one of the application of the Gauss's theorem, that is to find the electric field to a uniformly charged thin spherical shell. So we have to consider a spherical shell of radius r and the charges are uniformly distributed. So at 3 points we want to calculate the electric field. So first point we want to calculate the electric field outside the shell. Second point on the shell. Then third point inside the spherical shell we want to calculate. So these are the 3 points we want to discuss today. So first point we want to calculate the electric field outside. So now we just consider this is the Gaussian surface and this is the spherical shell of radius capital R. Now we want to calculate the electric field at point P, that is outside the shell, and it is of radius r from the center to that point P, the distance we are taking as r. So now we can find what will be the closed integral vector E dot vector ds, that is equal to closed integral E ds cos theta. So here question, how will you find the angle theta? Theta is the angle between the electric field and the area vector. So first we can calculate what will be the direction between the electric field and the area vector. So first we just consider a small area, and we know that how to draw the area vector. It is always acting perpendicular to that surface and it is always acting in the outward direction. So we can say at this point the area vector is acting in this direction, and also what will be the electric field at that point. So it's a positively charged spherical shell and the electric field is acting radially outwards. So if you are considering at this point, electric field is also in the same direction. So we can write theta is equal to how much? 0. That means angle between the electric field and the area vector is equal to 0. So now we can substitute in this equation, that is integral E ds cos 0. So that is equal to E closed integral ds. So what will be that area, total area? We can take it as E into 4 pi r squared. So that is the closed integral vector E dot vector ds. Now we want to apply the Gauss's theorem. So we know that the Gauss's theorem means what? The total electric flux over a closed surface is equal to 1 by epsilon naught times the net charge enclosed by that Gaussian surface. So now here we can consider integral E dot ds is equal to the q by epsilon naught. And what about the value of integral E dot ds? We already calculated. So what will be that value? That is E into 4 pi r squared is equal to q by epsilon naught. So electric field E is equal to 1 by 4 pi epsilon naught into q divided by r squared. So this is the equation for the electric field at a distance r from the center of the spherical shell. So if you want to calculate the electric field outside, that is at a distance r, and that is greater than what? Capital R. Capital R is the radius of what? Spherical shell. So this is the equation to find the electric field outside the spherical shell. That is, E is proportional to 1 by r squared. So suppose if we just consider the entire charge, suppose if we are keeping at this point Q and we are keeping the same distance, r. So what will be the electric field at this point P due to the charge Q? So that equation for the electric field is 1 by 4 pi epsilon naught into Q divided by r squared. Now if we are considering the spherical shell, in that case also we are getting what? The same result. So we can conclude that for points outside the spherical shell, the electric field due to a uniformly charged shell is as if the entire charge of the shell is concentrated at its center. Okay, that means for points outside the shell, the electric field due to a uniformly charged shell is as if the entire charge of the shell is concentrated at its center. So this is the electric field at outside the shell is equal to 1 by 4 pi epsilon naught into q by r squared. Now the second point we can calculate on the surface of the spherical shell. So already we calculated the electric field outside, that is at a distance r. Now we want to calculate r becomes equal to what? Capital R, that is on the surface of the spherical conductor. So electric field equation we can write 1 by 4 pi epsilon naught into q divided by that r becomes now the radius only, so that is capital R square. So this is the electric field on the surface of the spherical shell. Now we can write the same equation in terms of the surface charge density. So surface charge density sigma is equal to q divided by 4 pi r squared. That means the charge per unit area, that will gives what? The charge density. So we can write the same equation in terms of the surface charge density. So q by 4 pi r squared, that is surface charge density sigma. So electric field we can represent it as sigma divided by epsilon naught. So that is the electric field on the surface of the conductor. Electric field is 1 by 4 pi epsilon naught into q by r square, or in terms of the charge density is equal to sigma divided by epsilon naught. Now comes the third point, to find the electric field inside the spherical shell. So now this is the Gaussian surface. Now we have to consider the Gaussian surface inside the spherical shell. And this distance we can take it as r. And that r is less than capital R. That means inside the spherical shell. So now we just applying the Gauss's theorem, vector E dot vector ds is equal to what? Q by epsilon naught. So now we have to calculate what will be the net charge enclosed by this Gaussian surface. So usually we know that charges is distributed. Where it is distributed? On the spherical shell only the charges are distributed. So the net charge, or there will be no charge enclosed in the Gaussian surface. So we can take the net charge inside is 0. So we can write what? Integral E dot ds is equal to 0, or electric field is equal to 0, because there is no net charge inside the Gaussian surface. The charges is distributed outside the Gaussian surface only. So net charge becomes what? 0. So electric field is equal to 0. So these are the 3 points to find the electric field. So first point, we calculated the electric field outside. So electric field outside, we got the equation as E is equal to 1 by 4 pi epsilon naught into q by r squared. And in the second case, on the surface, we will get 1 by 4 pi epsilon naught into q by r squared. And in the third case, inside the spherical shell, electric field is 0, because the net charge enclosed in that Gaussian surface is equal to 0. Thank you.